Hi there. We will be dealing with the subject called electronic product design, and in that, this lecture is dedicated for Unit 5, that is product debugging and testing. So, shortly, we will be looking at what are the key contents of this unit. It is having these types of debugging, techniques for troubleshooting, characterization, electromechanical components, passive components, active components, active devices, operational amplifiers, analog to digital conversion, digital component, inspection and test of components, simulation, prototyping and testing, integration, validation and verification, and lastly EMI EMC issues. So basically here the terminology that is debugging is very important, and hence the testing. So you must have the basic knowledge of what do you mean by system design, circuit design, PCB design, packaging, software and hardware, all the knowledge from the previous 4 units. And this unit specifically provides you the principles used for debugging and testing of the components. Here the main focus is to understand how components function and fail, how testing and debugging is important to make the product reliable. So basically debugging is the art of testing of a hardware design and any embedded software to obtain desired performance and the functionality. Debugging is important element of the overall design strategy. It can save a lot of time and money when it comes to the deployment of the end design in the field. Debugging of the hardware side of an electronic product is only half the battle. The intelligence of the product and the source of real sustainable differentiation is the embedded software coding running on a processor in the design. It is this code that makes the product smart on the basis of the product's functionality. Debugging is the art of diagnosing errors in the programs and determining how to them means how to correct them. Bugs comes in variety of forms including coding errors, design errors, complex interactions, poor user interface design, and system failures. In the beginning of debugging effectively, it requires that the problem has to be identified, looking at and apply the appropriate technique to eliminate this crisis. Bugs are found throughout the software lifecycle. The programmer may find an issue, a software tester might identify a problem, or the end user might report an unexpected result. Part of debugging effectively involves using the appropriate technique to get necessary information from the different sources of the problem reports. So here there are 5 important steps in the debugging, that is observe and characterize. Second, the brainstorm. Third, hypothesis. Fourth, test. And fifth one is repeat. So you can choose while explaining this in the exam. You must have to correlate all these 5 points with reference to an example. So the first one is the observe and characterize. So here it is it has been given main focus on the collection of the information by observation from the user. Now the second step is to think That is brainstorming, discussing possible causes with the stakeholders. Next one is the hypothesis. So you have to assume an hypothesis for the previous data. The fourth step is test. So you need to perform the test, that is device experiment based on the analysis. And the last step is repeat, that is reiteration of above steps till the bug is removed. So these are the important steps. We need to explain them with reference to an example. So with coding errors, the source of the problem lies with the programmer included the improper code. Some of the examples like failing to initialize a variable when absolutely required, then using the wrong variable names in the wrong places, skipping the check for the error return, disregarding adopted conventions, and calling the wrong function. So these are the possible examples of the coding errors. Software users readily see some design errors, while in the some cases design flaws make a program more difficult to improve, or these flaws are not apparent to the user. The obvious design flaws are the limitation of a computer, such as available memory, available disk space, available processor speed, and the input outputs of the devices. Complex interactivity bugs arise in the scenarios while multiple parts of a single program or multiple programs or multiple computers interacts. When the option is hard for the user to pursue, that user might report a bug. Occasionally, computer hardware simply fails, and it usually does so in wildly unexpected ways. Determining the problem lies not with the software itself, but with the computer on which it is usually com- complicated by the fact that the debugging the software may not have access to the hardware that shows the problem. It is very important to prevent the bugs at the initial place. If the programmer create the right code, but users cannot work with user interface, it might that the code not be well written. In short, a good debugger should keep an open mind about where the problem might lie. So, one must adopt some of the steps to reduce or to adopt the debugging techniques, like uses log files with the correct mindset, thinking of the similar situations, starting at the correct source, treat the user input with the doubt, change one thinking at a time, proper selection of the test suits, back out the changes that have no effect, attempt another port of the application. So here we will take an example. So the debugging generally involves, for example, visual inspection. So in that parameter, we have to focus on the dry solder, the broken wires, bent pin connections, damaged boards. So all possible ways to inspect for the debugging. Then the next issue is checking the continuity, checking the power supply, verify the schematic, verify the software, and some other second perspective for debugging. Now we will be looking at the troubleshooting. Troubleshooting is possibly the most difficult task of a computer professional. Frequently, the problem reported are just symptoms, not the cause. So it takes investigation to identify the real cause. There are some of the phases for troubleshooting. For example, the first phase could be defining the problem. The next phase is troubles in the hardware and software. And the last phase is conduct the repair, followed by confirming the results and documentation of the results. So as to troubleshoot, we need to consider various means or equipments for debugging, and that has to be studied. One must understand the specifications of the debugging instruments. The instruments like oscilloscope, digital multimeter, function generator, power supply, logic analyzer, in-circuit emulators, and so on. As far as the phases of troubleshooting are concerned, in the very first phase, that is defining the problem, is the most critical and often most ignored. Without a complete understanding of entire problem, it is a great deal of spending time on the symptoms instead of the cause. The tools required for this phase are pad of copper, pen, good listening skills. Following are the specific questions to help and identify the problem and list out that lead up to the failure. That is, what does the problem or error look like? Then, when first notice, when did first notice the problem error? Any changes made to software or hardware can again reproduce the same problem or error. Are there any error messages received on display? Are there current backups for the system and data files available? So one must take the answers of these questions and start accordingly defining the problem. In the next phase, that is troubles in hardware and software, the best method is to eliminate any obvious problems and work from the simplest problem to the more complex. The basic troubleshooting technique simple steps can be adopted as visual inspection, checking of a dry solder and broken wires, bent pin connectors, checking of damaged PCB, the continuity test, the power supply, the schematics of circuits, also verifying the software and second perspective are the ways as we have seen earlier. The other means or equipments for debugging that we have listed over here. So we need to understand or we must know the specifications of all those enlisted instruments for troubleshooting. The CRO probes are also important and play a crucial role in measuring bugs in the electronic circuits. The impedance matching of CRO probe is very important for correct measurements. The oscilloscope probes can be categorized into a number of different types, that is, active, passive, and so on. The oscilloscope enables the waveform to be viewed in the graphical format. To enable the oscilloscope, To connect to the required points, oscilloscope probes or scope probes are required. The passive probes of oscilloscope. This type of probe is one that is most widespread, having widespread use. It only includes the passive elements and may provide 1:1, that is straight through the connectivity from the point under test to the scope input. Other types may provide a different degree of attenuation. Scope probes are generally classified according to the level of attenuation of the signal. The types including 1x giving 1:1 attenuation ratio, 10x giving 10:1 attenuation ratio, and 100x giving 100:1 attenuation ratio are available. The 10x scope probes use a series resistors of 9 megaohm to provide 10:1 attenuation when it is used with the 1 megaohm input impedance of the scope itself. The 1 megaohm impedance is the standard impedance used for oscilloscopes. The 10x oscilloscope probes also allow same compensation for the frequency variation present. A capacitor network is embodied into the probes as we refer the circuit diagram. The capacitor connected to the ground can be used to equalize the frequency performance of the probe. By attaching the oscilloscope probe to this, with a quick adjustment can be made. However, if the leading edges of the spike and rise too high, falling back to the required level, then the high frequency response has been enhanced and this needs to be adjusted. It is generally accepted that general purpose, that is mid to low frequency, that is less than around 500 megahertz measurement, high impedance passive probes such as 10:1 are the most suitable option. Often the choice of scope probe that is used will depending on what is available in the lab. However, for the most application, 10x probe is the best all-round type of probes. Coming to the next, active oscilloscope, active probes of the oscilloscope. Although 10x probes are widely used because their superior response, they are not able to provide all the performance that may be needed for some applications. By using active electronic circuit in the remote end of the oscilloscope probe, it is possible to offer a very high level of performance. Active probes are specially developed integrated circuit. By placing these chips right at the point at which the signal is probed, it enables the signal to be preserved during its transition from the point at which it is sampled to the point of the oscilloscope, in some instances using differential techniques. In this way, the signal integrity is maintained despite the fact that it may have a fast rise time, may have a low signal level, or require high input impedance at the point at which it is sampled. Not only it is the input resistance, it is having the input resistance very high, but more importantly, the most capacity, the input capacitance is very low, with the capacitance normally providing the limiting factor. The reduction in the capacitance enables sensitive waveforms to be measured for more accurately. So we must now able to explain the category of the problem and what are the symptoms. For example, if I consider electrical power, so the problem can be associated with electric utility, the fuse box, wiring plugs, cords, power supply and power connectors. So one must identify what are the symptoms of the said problem. Next example is the connectivity. So connectivity, the problem could be arised from external and internal cables, okay, and symptoms like devices not working and so on. So likewise, we need to work on the possible categories like booting the memory, the mass storage device, input output, your operating system, then various applications, the device drivers, memory management, configuration, network, and operator interface. So one must identify the problem, one must identify the symptom, and then we could be able to troubleshoot that problem in a nice way. Now, coming to the third phase, the last phase that we have seen, that is troubles in the hardware and software. Now, we must consider the next step is repairing that problem. So, the process of elimination begins. So, for that purpose, we have to make a plan. So, create a planned approach to isolate the problem based on the fact at this point. Plan should start with the most obvious or easiest solution to eliminate and move forward. The first step of any plan should be to document and the backup. Once the plan is created, it is more important to follow it through. The programmer should document the every action taken and the results at every step. If while executing the plan, after locating the problem, either repair or replace the defect. If the problem is software oriented, be sure to record the before and after changes. The next phase is the confirmation of the result. For that purpose, we must be sure that the problem no longer exists. Ask the user to test the solution and confirm the client satisfaction. And finally, the last phase is documentation of the results. Document the problem and the repair with experience in troubleshooting. Keep a copy of the repair procedure in the technical library. This is the way to build, maintain, and share experience. The record can also help if there are later questions about service performed from a client or insurance company. The next topic is characterization. A characterization is the concept of creating characters for a narrative manner. In computer programming, a characterization test means to characterize the actual behavior of existing piece of software and therefore protect existing behavior of the legacy code against unintended changes via automated testing. The goal of characterization test is to help developers verifying that the modification made to a reference version of a software system did not modify its behavior in unwanted or undesirable ways. They enable and provide a safety net for extending and refactoring code that does not have adequate unit tests. When creating a characterization test, one must observe what output occurs for a given set of inputs. Unfortunately, as with any testing, it is generally not possible to create a characterization test for every possible input and output. It is often sufficient to write characterization tests that only cover the specific inputs and outputs that are known to occur, paying a special attention to the edge cases. One of the interesting aspects of characterization tests is that since they are based on existing code, it is possible to generate some characterization tests automatically. An automated characterization test tool will exercise existing code with a wide range of relevant and random input values, record the output values, and generate a set of characterization tests. When the generated tests are executed against a new version of code, they will produce one or more failures or warning if the version of the code has been modified in a way that changes previously established behavior. The characterization means testing under different environments to evaluate their performance and margin of the performance for the following items, like circuits and schematics. Next one is systems and processes, components and equipments. Next, temperature or vibration or shock tests, behaviors, effect of the test based on reliability, simulation of the components for characterization, model development from previous experience. Now moving to the next topic, electromechanical components. The term electromechanics combines electrical and mechanical processes drawn from electrical and mechanical engineering. Devices which carry out electrical operations by using the moving part are known as electromechanical. The term is usually referred to the devices which involves an electrical signal to create a mechanical movement or mechanical movement to create an electrical signal. There is always chance of bugs in such components which may create trouble in the design. The electromagnetic principles such as in relays which allows a voltage or current to control other. Oftentimes isolated circuit voltage or current by mechanically switching the sets of contacts and solenoids by which a voltage can actuate a moving linkage as in solenoid balls. Electromechanical components are used specifically in circuit protection components. Next is cooling products and thermal management. Next, motors, drives and rotating equipments. Next, relays and solenoids. Next, sensors, transducers and audio components, and in the switches. The next point is passive components. Electronic components can be classified as passive components and active components. The strict physics definition treats the passive components as one that cannot supply energy to themselves, whereas a battery would be seen as an active component since it truly acts as a source of energy. Passive components cannot introduce net energy into the circuit. They also can't rely on the source of power except for what is available from the circuit they are connected to. As a consequence, they cannot amplify, although they may increase a voltage or current. Passive components include two-terminal components such as resistors, capacitors, inductors, and transformers. In electrical, computer, or storage system, passive components are those that do not require electrical power supply to operate. This could include the chassis, capacitors, resistors, or enclosures that do not require electrical power supply to operate. Those devices or components which do not require external source to their operation is called as passive components. For example, resistor, capacitor, inductors. Passive components are electronic components that do not require a source of energy to perform their intended functions. In an electrical and computer or storage system, active components are those that requires electrical power to operate. This could include the power supply, fans, storage devices, transistors, diodes, and other integrated circuits. Those devices or components which requires external source to their operations are called as active components. For example, the list as per the list, here we are having the diodes, special purpose diodes, bipolar junction transistors, field effect transistors, analog and digital integrated circuits, displays, detectors and emitters. The next point is the active devices. An active device is any type of circuit component with the ability to electrically control the flow of the process. In order for a circuit to be properly called electronic, it must contain at least one active device. Active devices includes but are not limited to vacuum tubes, transistors, SCRs, and triacs. A cause might be made for saturable reactor to be defined as an active device since it is able to control an AC current with a DC current. The practical benefit of active devices is their amplifying ability. Whether the device is voltage controlled or current controlled, the amount of power required of the controlling signal is typically far less than the amount of power available in the controlled current. Because of this controlling and controlled powers, active devices may be employed to govern a large amount of power by the application of small amount of power. This behavior is known as amplification. An operational amplifier is the best example of active device. Now we will be looking at the operational amplifiers. So what is an operational amplifier? An operational amplifier, generally called as op-amp, is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single ended output. In this configuration, an op-amp produces an output potential which is relative to the circuit ground that is typically hundreds of thousands of times larger than the potential difference between its input terminals. The popularity of operational amplifiers as a building block in analog circuits is due to its versatility. Due to negative feedback, the characteristics of operational amplifier circuit, its gain, input and output impedance, bandwidth, etc. are determined by external components and have little dependence on temperature coefficients or manufacturing variations in the op-amp itself. An op-amp is used in a vast array of consumer, industrial and scientific devices. Op-amp may be packaged as components or used as elements of more complex integrated circuits. The output voltage signal from operational amplifier is the difference between the signals being applied to its two individual inputs. In other words, an op-amp output signal is the difference between two input signals, as the input stage of an operational amplifier is in the fact a differential amplifier. So we will now look at the structure and the operation of the differential amplifier. Here, the circuit for differential amplifier is shown in a generalized form with the two inputs marked V1 and V2. The two identical transistors TR1 and TR2 are both biased at a same operating point with their emitters connected together and return to the common rail -VEE by the way of the resistor RE. The circuit operates from a dual supply plus VCC and minus VEV, which ensures a constant supply. The voltage that appears at the output Vout of the amplifier is the difference between two input signals, as the two base inputs are in antiphase with each other. So, as the forward bias of the transistor TR1 is increased, the forward bias of the transistor TR2 is reduced and vice versa. Then if the two transistors are perfectly matched, the current flowing through the common emitter resistor RE will remain constant. Like the input signal, the output signal is also balanced, and since the collector voltage either swing in antiphase or in phase, the output voltage signal taken from between the two collectors is assuming a perfectly balanced circuit. The zero difference between the two collector voltages. This is known as the common mode of operation, with the common mode gain of the amplifier being the output gain when the input is 0. Operational amplifiers also have one in output of a low impedance that is referred to a common ground terminal, and it should ignore any common mode signals. That is, if an identical signal is applied to both the inverting and non-inverting inputs, there should no change to the output. However, in real amplifiers, there is always some variation, and the ratio of change to the output voltage with regards to change in the common mode input voltage is called as the common mode rejection ratio, CMRR. Operational amplifiers on their own have a very high open loop DC gain. By applying some form of negative feedback, operational amplifier circuit with very precise gain characteristics that is dependent only on the feedback used. An operational amplifier only responds to the difference between the voltages on its two input terminals, known commonly as differential input voltage, and not to their common potentials. Then if the sum voltage potential is applied to both the terminals, the resultant output will be 0. An operational amplifier's gain is commonly known as the open loop differential gain and is given as a symbol A0. The next diagram shows the equivalent circuit of an ideal operational amplifier with a blue ink. So, the parameters for the idealized characteristics of an operational amplifier must exhibit: the open loop gain must be infinite, the input impedance must be infinite, the output impedance must be 0, the bandwidth must be infinite, the offset voltage must be 0. So one should emphasize on all these factors regarding with the parameters of an ideal operational amplifier, and what are the key constraints that one should understand. It is observed from throughout this operational amplifier section that we can connect add-on registers to a basic operational amplifier to produce various inverting and non-inverting outputs and configurations along with their respective gains. So these are called as the basic operational amplifier building blocks. So all these constraints have been already covered in the subject called linear integrated circuit, but we will see what are the constituents of this list. The first one is the voltage follower, where V out equals to V in. Then the next one is the op-amp as an inverter. The third one is the non-inverting amplifier. The fourth one is the inverting amplifier. The fifth one is the bridge amplifier. Sixth one is the voltage adder. Seventh one is voltage subtractor. And eighth one is the comparator. So all above are the lists. So one should take into account what is the configuration with reference to the connections and the feedback paths and so on. The next important topic is analog to digital conversion. Analog to digital conversion is a system that converts a continuously variable signal with alternating its essential contents into multi-level signal. Analog to digital converter inputs consists of a voltage that varies among a theoretically infinite number of values. For example, if you take a sine wave, the waveform representing human speech and signals from a conventional television camera. The output of ADC, in contrast, have the defined levels or states. The simplest digital signal have only two states in binary from zeros and ones. Digital signals are more efficiently than the analog signals, largely because digital impulses, which are well defined and orderly, are easier for electronic circuits to distinguish from noise, which is messy. The advantage of digital modes in communications, computers talk and think in terms of binary digital data. While a microprocessor can analyze analog data, it must be converted into digital form for the computer to make sense of it. The conversion involves quantization of the input, so it is necessarily introduces a small amount of error. Instead of doing a single conversion, an ADC often performs the conversions periodically. The result is a sequence of digital values that has been converted from a continuous time and continuous amplitude analog signal to discrete time and discrete amplitude digital signal. An ADC is defined by its bandwidth and its signal to noise ratio. The actual bandwidth of an ADC is characterized primarily by its sampling rate and to a lesser extent by how it handles errors such as aliasing. The dynamic range of an ADC is influenced by many factors, including the resolution, linearity, and accuracy, and jitter. The dynamic range of an ADC is its effective number of bits, the number of bits of each measure it returns that are on average not noise. An ideal ADC has an ENOB, that is effective number of bits, equals to its resolution. ADCs are chosen to match the bandwidth and required signal to noise ratio of the signal to be quantized. If an ADC operates at a sampling rate greater than twice the bandwidth of the signal, then perfect reconstruction is possible given an ideal ADC and neglecting the quantization error. The presence of quantization error limits the dynamic range of even an ideal ADC. However, if the dynamic range of ADC exceeds that of the input signal, its effects may be neglected, resulting in an essentially perfect digital representation of the signal. An ADC may also provide an isolated measurement such as electronic device that converts an input analog voltage or current to a digital number proportional to the magnitude of the voltage or the current. However, some non-electronic or only partially electronic devices such as rotary encoders can also be considered ADCs. The digital outputs may use different coding schemes. Typically, the digital output will be a 2's complement binary number that is proportional to the input, but there are other possibilities as well. An encoder, for example, might output a gray code. The inverse operation is performed by digital to analog converter, which gives the analog value at the output. The audience here might be familiar with the working principles, the types and the important parameters of the ADCs earlier, but still one should emphasize the listed parameters over here while studying the analog to digital converters. The first one is the quantization error, next one the accuracy, the non-linearity, the jitter, what is the sampling rate, how to avoid aliasing, then oversampling, the relative speed and the precision of the ADC, and finally sliding scale principle. Also, the audience might be aware of various types of ADCs as listed over here. The direct conversion ADC or flash ADC, the successive approximation ADC, RAM compare ADC, delta encoded ADC, pipeline ADC, delta sigma ADC, time stretch ADC. There are varieties of applications of ADC because moving to the digital domain gives us some kind of a benefit over analog. For example, if you take a signal processing problem, while adding the signals, if you take two analog signals and you want to add those signals, then there is a large efforts and some of the components are involved to make sense of the addition of two different analog signals. But when you digitize those signals, you need not to worry about any component or anything while making sense of addition of those two signals. So ADCs are having a vast applications and mainly in signal processing techniques. For the digital components, we are having variety of applications, but still digital components may face various sorts of problems typically when operating at higher frequencies. So we must understand or we must focus on such problems and we have to overcome such problems. So first of all, let us see what points we need to consider while working with the digital components. So at high frequencies, digital components face problems like ground bounce, transmission line constraints, phase jitter, and propagation delay. So one must take a note while operating the digital components at the higher frequencies. In the inspection and test of components, the experienced and tenured inspectors conduct a visual inspection and authenticity verification of all incoming material. So in this, the packaging examined with reference to weighted and checked for damage, taping condition and inspected dented package, etc. Original factory seal versus non-factory seal. Then we must have to verify the shipping documents. Then manufacturer's details, the quantity, date code verification, then moisture barrier protection verification, vacuum sealed and humidity indicator with specification, products and packaging, body marking inspection, physical condition inspection, and any other visual irregularities found. Once visual inspection is completed, products are escalated to the next level, electronic components engineering inspection for review. Highly skilled and trained engineers receive the components for evaluation at the microscopic level to ensure the consistency and the quality. Any suspect parts or discrepancies discovered in the visual inspection process will either be verified or discounted by taking a product sampling of the material or the parts. The engineering inspection process for electronic components includes verification of the labels, extensive marking, permanency tests, additional photos taken and catalogued, referencing ERAI and internal databases, review visual inspection findings and notes, manufacturer's logo and date log verification, purchase and sales order numbers verification, moisture sensitivity level and ROHS status, review and comparison to manufacturer datasheet. Coming to the simulation is the limitation of the operation of the real world process or system over time. The act of simulating sometimes first requires that a model be developed. This model represents the key characteristics or behaviors of the selected physical or abstract systems or processes. The model represents the system itself, whereas the simulation represents the operation of the system over time. A computer simulation is an attempt to model a real life or hypothetical situation on a computer so that it can be studied to see how the system works. By changing the variables in the simulation may be made about the behavior of the system. It is a tool to virtually investigate the behavior of the system under study. Simulation is used in many contexts, such as simulation of technology for performance optimization, safety engineering, testing, training, education, and video games. Often, computer experiments are used to study simulation models. Simulation is also used with the scientific modeling of a natural system or human system to gain insight into their functioning. Simulation can be used to show the eventual real effect of alternative conditions and courses of reactions. Key issues in simulation includes acquisition of valid source information about the relevant selection of key characteristics and behaviors, the use of simplifying approximations and assumptions within the simulation, and fidelity and validity of the simulation outcomes. Virtual simulation represents a specific category of simulation that utilizes simulation equipments to create a simulated world for the user. Virtual simulation allows user to interact with the virtual world. Prototype is an early sample model or release of the product built to test a concept or a process or to act as a thing to be replicated or learned from. It is a term used in variety of contexts including semantics, design, electronics, and software programming. A prototype is designed to test and try new design to enhance precision by system analytics, and users. Prototyping serves to provide specifications for real-world working system rather than a theoretical one. In some workflow models, creating a prototype is the step between formalization and the evaluation of an idea. It is important to realize that by their very definition, prototypes will represent some compromise from the final production design due to difference in material processes and design fidelity. It is possible that a prototype may fail to perform acceptably, whereas the production design may have been sound. It is possible to use prototype testing to reduce the risk that a design may not perform as intended. However, prototypes generally cannot eliminate all the risk. There is a pragmatic and practical limitations to the ability of the prototype to match the intended final performance of the product, and some allowances and engineering judgments are often required before moving forward with the production design. In electronics, prototyping means building an actual circuit to a theoretical design to verify that it works and to provide a physical platform for debugging it if does not. The prototype is often constructed using techniques with the result being a circuit that is electrically identical to the design but not physically identical to the final product. A technician can quickly build a prototype using various techniques, but for volume production, it is much faster and usually cheaper to mass produce custom printed circuit boards than to produce these other kinds of prototype boards. The proliferation of quick turn PCB fabrications and assembly companies has enabled the concept of rapid prototyping to be applied to the electronic circuit design. It is now possible, even with the smallest passive components and largest fine pitch packages, to have boards fabricated, assembled, and even tested in a matter of days. Software testing is an investigation conducted to provide stakeholders with an information about the quality of the product or service under test. Software testing can also provide an objective, independent view of the software to allow the business to appreciate and understand the risk of the software implementation. Test technique includes the process of executing a program or application with the intent of finding the software bugs. It involves the execution of a software component or system component to evaluate one or many properties of interest. Software testing can provide objective, independent information about the quality of the software and risk of its failure to the users. The software testing can be conducted as soon as executable software exists. The overall approach to the software development often determines when and how testing is conducted. Integration is the platform or stage at which designer has to combine all concerned parts of the product so that they all should work like a team. Nearly every man-made object that comes into contact with was likely the result of a team effort, but in the production development world, as products continue to grow more complex, it requires interactions and understanding amongst all concerned parts of the product. Companies today are under ever increasing the pressure to differentiate through feature, function, manufacturing, or materials for their integration. No longer can products simply be passed down an assembly line of firms receiving strategic insight, research, industrial, mechanical, electrical, and other development work separately. Today, development programs must allow transparency across a team, enabling each member to become highly involved with each step. Only then it can integrate the goals, expertise, and methodologies successfully. Basically, this enables opportunities for innovation while helping to carry the vision all the way through to the production while curtailing late compromises. Integration of design model with process and scheduling information in the real time is necessary in order to increase product quality, reduce the cost, and shorten the product manufacturing cycle. Verification and validation are independent procedures that are used together for checking that a product, service, or system meets the requirements and the specifications and that is fulfills its intended purpose. The words verification and validation are sometimes preceded with independent, indicating that the verification and validation is to be performed by disinterested third party. Validation, the assurance that a product, service, or a system meets the needs of a customer and other identified stakeholders. It often involves acceptance and suitability with external customers, contrast with verification. Now, the verification, the evaluation of a whether or not a product, service, or a system complies with a regulation, requirement, specification, or imposed condition. It is often an internal process in contrast with the validation. Verification is intended to check that a product, service, or a system meets the set of design specifications. In the development phase, verification procedures involve performing a special test to a model or simulate a portion or with the entirely of the product, service, or a system, then performing a review or analysis of the modeling result. In the post-development phase, verification procedures involves regularly repeating tests specifically to ensure that the product, service, or a system continues to meet the initial design requirements, specifications, and regulations as time progresses. This is often an internal process. Validation is intended to ensure a product, service, or a system result in a product, service, or that meets the operational needs of the users. For a new development flow or verification flow, validation procedures may involve modeling either flow and using simulations to predict faults or gaps that might lead to invalid or incomplete verification. It is entirely possible that a product passes when verified but fails when validated. This happens when, say, a product is built as per the specification but the specification themselves failed to address the user's need. This often involves acceptance of fitness for purpose with end users and other product stakeholders. The electromagnetic interference or electromagnetic compatibility control test and measurement facility supports engineering development and EMI EMC measurements and provides the evaluation and certification testing of a crew, flight, or ground support equipment, including but not limited to communication, instrumentation, biomedical, guidance and navigation, computations, and robotics. It is the branch of electrical science which studies the unintentional generation, propagation, and reception of electromagnetic energy with reference to unwanted effects that such energy may induce. The goal of EMC is the correct operation in the same electromagnetic environment of different equipment which uses electromagnetic phenomena and the avoidance of any interference effect. In order to achieve this, EMC pursues two different kinds of issues as emission and susceptibility. The issues are related to the unwanted generation of electromagnetic energy by some source and to the countermeasures which should be taken in order to reduce such generation and to avoid the escape of any remaining energies into the external environment. Susceptibility or immunity issues, in contrast, refer to the correct operation of electrical equipment referred to as the victim in the presence of unplanned electromagnetic disturbance. So while working with EMI and EMC issues, we must consider the following parameters like conducted emissions, conducted susceptibility, radiated emissions, and radiated susceptibility. So in this way, we have covered this chapter, but for more details, you should refer. Thank you for patiently listening to this lecture.